I'm just waiting to make sure I am live on YouTube. Sometimes there's a small delay with that, and I have this pending paranoia from quite a few days that always makes me double check things. I can hear and double echo, which means we're live on both platforms. That's awesome. Welcome back, everybody. This is, I think, the third reading group. Feels like it's been going on for a while because we've been learning so many topics. It's great to see everyone back. Thanks for joining us again. We've been doing this for quite a few weeks now, and I'm excited to continue learning further with you all. Uh, if you're new, or if this is your first Keras reading group, or if you're watching the recording for the first time, we've been reading this incredible book called Deep Learning with Python. We're halfway through it. That shouldn't stop you from joining us. We're still in the beginning of learning Keras. We'll actually just start going into the advanced topics, if I may, this week. So you're still early. You're welcome to join. You're welcome to ask as many questions as you want. My only request is ask as many questions as you want. No question is too stupid. All questions are welcome. If you're watching a recording on YouTube, leave a comment below. I always monitor them. I'm happy to come back and leave any answers that you to any questions that you might have. So to remind you, last week we learned about introduction. We got an introduction to the Keras API, and we understood the basics of machine learning. We learned what makes deep learning really interesting. How does it stand out against traditional quote unquote machine learning? And we, of course, started the series with an Ask Me Anything with Francois. Just wanted to remind you, if in case you haven't watched that. My tongue is really rolling off today, so I need more chai. This happens during the winters to me a lot. It's quite cold. So here's the agenda for today. I want to go into a deep dive of Keras. I'm actually just following the book and trying to add a few things here and there. We'll be learning about what are convolutional neural networks, what makes them so cool, what is image augmentation, and if you've been around in the Twitter space recently, you would know that oops, it's it's gone down the list, but I wanted to point out that ConvNext is a really interesting paper that has been it's fourth on the list, so that's not too far. It's received 2500 stars in like under a week. We'll be understanding how to implement this architecture in Keras. And I won't be doing that. I got a lot of help from my incredible colleague, Shomik. I'll be using his implementation. We actually read the paper together and he instantly implemented this. So we'll be learning how to implement this architecture, a cutting edge architecture. As I said, this paper came out just 12 days ago, so it's quite recent. So we're at that point already where we can go off, learn one of the most recent architectures in Keras. We can build that, and I'm quite ambitious with the agendas, but I hope to get to that point today. We will also be understanding how to log experiments in weights and biases. We're at the point where we can start experimenting a lot. So I'll be showing you the DB callback. And if you don't know what callbacks are, I do plan to cover it as well. So here's the agenda for today. There'll be a recap for 5 to 10 minutes. Then we'll an ambitious goal, but we'll try to get up until chapter 9. So cover up until from chapter 7 to 9. I'll try to explain image augmentations, why are they necessary, why are they important, and then we'll go to the next implementation. And throughout the session, you all must be familiar. I keep taking breaks to answer any questions, so please keep the questions coming. Quick recap from last session. We learned how is deep learning different from traditional learning. There are fewer knobs to turn. You just need to set a bunch of hyperparameters. It's lesser of an effort, but it's also trickier to implement. It takes longer to train, but it's more accurate. There's this nice trade-off. And as a practitioner, you'll always be challenged to pick the right option. And I don't have a suggestion on how to do that. We also did a case study where I brought up an suggestion of how you would build an app from the ground up. So, chapter 6 of this book, Deep Learning with Python, talks about the steps in the life cycle of model creation, steps in the life cycle of machine learning. So, the case study was understanding, let's say, if you were hired at a company like I don't know, Postmates, Uber Eats. How would you create that app? And I had this vague business idea that me and the audience discussed, you all and me discussed. So that was quite interesting as well, to me at least, to go through that discussion. If you haven't watched that, I would encourage you to check that out just to understand what are the steps in building a quote unquote real world app. And we also got a vanilla introduction to the Keras API. I always suggest homework. Sometimes some of you end up doing it, sometimes you don't. It always makes me happy when I see someone doing a suggested homework. But this was the suggested list. I wanted to suggest creating a MVP of the exercise that I just mentioned. I suggested watching a recent paper summary or just porting over a model from PyTorch to Keras. It can be of incredible learning, and I'm sure many people are familiar with this fact. But if you're not, I would encourage you to really try this, because all of us are at that stage where you can really implement a cutting edge paper, a latest deep learning paper from scratch in Keras. And I'm assuming every one of us joins this to learn to have a career in this field or to improve our skills. In my opinion, this is one of the best ways to actually improve your skills in deep learning. So I just wanted to remind everyone, hey, that's the homework. Consider doing it or don't. It's totally up to you. So again, we've gone through chapter 1 to 6, somewhere up until chapter 7 as well. We actually started going through it. Now we'll aim to cover working with Keras, introduction to deep learning for computer vision, and advanced deep learning for computer vision. So again, an ambitious agenda, lots of things to cover. But again, my focus is to keep it high quality. So if we have more questions or topics to discuss, I'll focus on that first. Setting up the stage for why are convolutions important. First topic in the 8th chapter is convolution. So I'm skipping ahead to give some theoretical introduction. Now, here's the problem with fully connected neural networks. They're really prone to overfitting. If you keep, this is true to any architecture, but they are quite prone to overfitting. They are positionally dependent. So if you want to find out where am I in this, so if you want to create a SIEM detector and you want to point me out in this image, if this image changes a little bit, or if I move around in the image, the fully connected neural network, if you remember the weights that we train on, they will have a hard time reconfiguring themselves because it's positionally dependent. It's not positional invariant. And that's what CNNs solve. That's a problem that CNNs address. They are positional invariant. So the goal is to be able to detect SIEM anywhere in this image. And that is what we'll achieve with CNNs. And of course, they have too many parameters. We were looking at one of the smallest data sets. It's almost the hello world in machine learning. I think we were looking at MNIST and CFAR, and we already saw that we were in the range of millions of parameters. So that is quite a lot of parameters. So when we create fully connected neural networks, we face these problems. How do we fight that? How do we address those? We look at convolutions. So how do convolutions work? Let's go back to this paper that I had addressed in the first lecture. Let me drop this link, highlight it. So there's the link if you want to check the paper out. You don't need to read the paper. I'll just give you the gist. This is a paper by Zeiler and Fergus, and they showcased us what does a convolutional network actually learn. So I'll give you a second to look closely across these layers. What they've done is they've visualized every single layer inside of a neural network. So as you can see, we're trying to learn general world objects, right? We see if you go towards the last layer, we're trying to predict humans. I see a dog. I see some food cans. Maybe is that a keyboard? I'm seeing a close up of a bicycle. So a lot of real world things, right? And neural networks consist of a lot of layers. Inside of the first few layers, we're learning about colors. We're learning about the basics of shape. So we see circles, we see edges. Then towards the later end, we start seeing more complex shapes. We can see a outline of a car tire that looks like that to me. We can see a person, and towards the furthermore end, then we can understand what a dog is. So we see a silhouette of a dog. We can see more complex images. So layer by layer, these architectures understand more and more details. So as you go deeper inside of a CNN model, inside of a CNN architecture, you start learning more details about the object, about the thing that's of interest to the model. So here's the intuition how they work, right? With every layer, they try to understand one layer of abstraction. And towards the later end, they hopefully, if you've done all things right, and if you've made a sacrifice to the GPU gods of enough cloud compute credits, you'll might be able to predict the right thing inside of the image. So that's how CNNs work. Now let's look at that in theory. They perform, here's the technical definition, they perform local operations on neighborhoods, it's translation invariant, and they have a lot fewer parameters. So here's an image. Quite funnily, this comes from the deep learning with PyTorch book. That's another session we hosted if you want to study from there, but that's where I copied this image from. So inside of every image, let's say we're trying to understand this bird. Every image, even my video, even the video you're watching right now, has three basic colors, RGB. Now, of course, if you've read any mobile phone or TV description, they have 16 million suggested potential colors. That's a different story, but the base color behind these is red, green, and blue. So every image would have these three colors. Now, what do we do from there? We take all of these, sorry, we take convolution operators, which we call kernels. These are matrices of a certain width. And we perform a matrix multiplication with all of these colors. So now the thing to remember here is, what do you see in this image? You see a person, you see few monitors, you see this computer. A PC or a PC just sees numbers. This is our human neural network trying to interpret things. But to a neural network model, an artificial neural network model, it just sees zeros and ones, or actually zeros up until 255s across three layers. So every image has RGB, red, green, and blue. Those values can range from 0 to 255, that denote the brightness. So if it's 255, 255, 255, if you've created any website, you would know that means white. And there would be associated hex value with that. Hopefully my teeth are white, so that would be a perfect array of 255, 255, 255, just like my chair in the background. But how do we go from these numbers to understanding what's inside of that image, right? Again, a computer just understands numbers, can't understand things beyond that. So what we do is we take these kernels that we multiply. Neural networks are a bunch of matrix multiplication. I gave that spoiler in the first lecture. We perform this matrix multiplication, after which we pass it through an activation layer. And then we start getting these outputs. What outputs? These outputs. These visualizations come from the convolution being performed with the input or whatever image we're passing to the model. Now, I know just from the fact of learning this that that's not good enough. So I'm stealing this explanation from Jeremy Howard, and I'll use his Excel sheet. Let me share the right screen again to explain this using Microsoft Excel. This was taken from FastAI, and I'll also share the link in a few minutes. So what I want to achieve here is showcase how do these work inside of Microsoft Excel. So what Jeremy has done here, or I might be confused. Rachel might have written this. Jeremy Howard and Rachel Thomas are the creators of FastAI, which is also one of the world's best deep learning course, in my opinion. So this comes from there. What they've done in this notebook, they've loaded up an MNIST number. How do I know that? It's 28 by 28. So that's where the skill of remembering these dimensions come from. So they've literally written, this looks like the logo of Swift, the logo of a bird, or this is how I would write 7 because that's how my writing is. That's what it looks like to me. This looks like number 7, right? So now what we want to do here is we want to predict that this is number 7, or we want to perform a bunch of convolutions. So again, what is a convolution? We have this filter that we convolve with the input image. So this output that we get is a matrix multiplication of the following. So we take this layer, it's a dot product. I apologize, it's a dot product of these. That's how you get a single number. But we take this filter or kernel and we convolve it with these numbers, which gives us this output. And then what do? We move one step towards the right and we do it for these numbers. You could change this. So you could, instead of going sequentially towards the right, so here's what we've done. We've multiplied in one area, move to the immediate right pixel. The thing to note here, what you're seeing right now is 1000, approximately 2000 by 1100 pixels. That's a lot of pixels. So even if you skip 1, 2, 3 pixels, no big deal, right? It's it's still 2000. You're just missing what, 600 out of 2000. You could do that, maybe compute faster. You can make the matrix multiplication faster. So the amount by which we jump pixels is called stride. That's how much we perform a stride by. And the size of the filter or kernel is called kernel size, quite unsurprisingly. These are the things we change inside of CNN when designing it. So we do this a lot of times, and then we get this first layer, which to me looks somewhat still like the 7 that I would write. I don't think anyone would write a 7 like this, maybe just me. And we also have another filter with which we perform this. You could imagine if this was an RGB image, you could have multiples of filters. And usually that is the case. So you have a lot of these with which you perform these actions. You get these outputs and then you do it again. So you have another filter, you perform this action again, and then you get this output. Now, what just happened, right? We just went from we 1/4 looks like. So we're skipping 4 pixels. So we 1/4 the conv to output. Why did that happen? Because if you look upwards, we're performing something known as max pooling. And this is the maximum out of these 4 numbers. So when some deep learning paper says you're performing max pooling, they're just taking the maximum of 4 layers. That's a max pool layer. Again, it's really easy to implement these ideas in code. That's why I would again remind you to check them out in a documentation because they make more sense maybe visually like this or in documentation. We're all coders here. I'm probably on the worst end of the scale. You all would be on the better end of scale for me, and we just want to get better in machine learning. So it's better to understand these concepts in code as well. So this would be maximum of a slice of these locations, right, in Python. So we do that for all of the possible pixels inside of this layer or this output that we got from performing this convolution. And then we would have a bunch of weights from which we can take a sum or take a softmax and get a final output, which would be the probability of is this a 7 or not? Let's say if we're trying to just predict a 7. That is again another detail that I'm not going in depth of, but this is how you perform a convolution. So when you have a neural network, this is what's happening inside of a CNN. This is a convolution operator. We take this kernel or filter. Quite unsurprisingly, we just do a bunch of matrix multiplication, which give us these outputs. We do that a bunch of times, and then we maybe perform a max pool, and we get a probability through some magic that we'll get into later on. So I'll take a pause to check out any questions. Ankit has a great question. I'll read that out. How do we decide the size of these kernels? So again, to remind everyone, since we've gone into a lot of jargon, this is the size of the kernel. Here it's 3 by 3. And another point that I want to add to Ankit's question, how would you decide what's tried to do, right? Through experimentation. It's again a lot of experiments. The paper I pointed out a while ago, ConvNext, actually does a really well job at this, and I'll point that out. It compares how this differs. But every single CNN architecture, every model that you import, right? If you can recall the famous names, think ResNet, think VGGNet. If you've been in the attention era, think Swin Transformer, think VIT. These have different strides. I might be wrong. They might be the same across all of the papers I mentioned, but it would be similar across or different across many different architectures. And again, the kernel size would be different. So the the number comes from experimentation or just following what's been going on. So Ankit, I would have a suggested homework for you to try, different filter sizes or kernel sizes and try different strides. Can you share this Excel sheet? Sure, I'll just point out the link in a few minutes. Any other questions by anyone? I don't see any questions yet, so I'll just double check. Otherwise, I'll continue further. Incredible. Now I have to go through the painful process of stopping sharing and resharing my screen. I've gotten much better at this. And every time I say that, I end up messing up. So hopefully I don't jinx it. Let's see if that worked. I think it did. Awesome. So this is what happens inside of a convolution operator and a convolutional neural network. We have the input image with which we take the convolutional kernel and we get an output. We perform a max pooling and then we get more outputs from which we finally, through more operations that will eventually cover, get a probability of what's actually happening inside of there. So I'm trying to think if I wanted to cover more things here. I don't believe so. Again, this was taken through the FastAI course, and I will now paste the link for the Excel sheet in the chat and highlight it. I would highly encourage everyone to try this out. In fact, it's a really good exercise to implement CNNs or any neural network inside of Microsoft Excel. It's a really visual tool. So let me close these tabs and get everything out of the way. I'll just continue further and quickly explain the other problems as well. So CNNs cover a lot of different problems, or they're used for a lot of different things. The example we've been looking at so far is simple image classification, which tells you if this is a hot dog or not hot dog. Hopefully my image would not be a hot dog. If not, you need to improve your skills because I'm not. Don't tell that neural network, don't embarrass me. Or it could be a dog versus cat classifier. It could be an ImageNet classifier, which will tell you what's inside of an image. But there are problems beyond that as well. So one of the other problems is it's really easy for the human brain to do this. But if you want to find me inside of the picture, how would you do that? Or how would you tell a computer to do that? One of the ways is, remember, the key point here is this is the zeros, ones, 255s, if you're being too technical, that the computer sees. How do you tell it what's inside of an image, right? Or how do you visualize it for yourself? You could draw a box around me. That's one viable approach, right? You could literally, if this image was printed out, you could take a pen, draw a circle around me. That's Sanyam. You can recognize me hopefully by now. If you want to tell everything inside of a pixel, you could do the same for everything inside of the image. Draw a circle around me, right, Sanyam? Draw a circle around that chair. Write down it's a chair. That's a couch. You could point out that's a couch. Or if you want to understand what's inside of an image, or if you want your neural network to understand what's inside of an image, you would label every single pixel with what it is. So, image segmentation, if you look closely with this image, this could potentially be from a self driving car. Sorry. We're coloring every single potential possible thing inside of this image with a different color. But the key thing to note here is all humans are blue, all cars are red, and trees are greenish. Those won't be trees, but we don't care that farther into the distance, maybe. Road signs are blue. So this is image segmentation because we're trying to segment every single pixel out of this image. We're trying to label that. The other problem I mentioned was object detection. So broadly speaking, these are the three problems that CNNs address, or three problems inside of computer vision domain. There are different ways of tackling this. There are a lot of architectures, but these are the three broad problems. We'll be going into depth into, I believe, image segmentation later on. So I won't cover these steps from now. I'll jump to chapter 7. So the first thing I've done here is so far we've learned what is a CNN. We've learned how it works by looking at an Excel implementation. And now we'll go back and understand the Keras functional API and then move towards learning what a CNN model implementation looks like inside of Keras. We'll also implement the cutting edge architecture I mentioned. So let's jump into that. And again, if there's any thing that's not clear, please ask a question, and I'd love to clarify it for you. I want to mention another thing. I've used weights and biases to track the experiments here, and I'll point everyone to this nice callback that we have implemented for Keras. You can check out this collab to learn about it. I won't be going into much depth. I'll just give a highlight of how that works. So now we're at the point where we want to learn about Keras. Last week we learned Keras was created out of this problem or necessity of having so many different APIs. We had TensorFlow, Theano, CNTK, MXNet. If you don't know those names, that's totally fine. This is from like 5 years ago, which is equivalent to 100 years in machine learning. That's where Keras originated from. So we learned about the history. But right now, it's at the stage where it's really mature. It's the official high level API for TensorFlow, which means there would have been a lot of thought of around what you can do with it. So there are different ways. There are ways around, hey, where you can take things and plug and play with them, right? There are ways where you can implement a new architecture. That's totally feasible. And if you're a researcher trying a very new idea, you could do that as well. So this chapter 7, introduces these different techniques, or how do you actually do these different things I mentioned about. So that's what we'll learn now. I have a lot of screens open through which I keep switching, which is why you see a small delay. The first way to build a Keras model is the sequential class. Now let's hop over here and see what sequential is. Took me to conv 2D layer. I don't want there. Don't want to go there. Or maybe I'll just explain through the collab itself. All right. So a sequential model is quite simple to implement. It just takes a list of layers you want to add. So what is a dense layer? We can look that up, or at this point, I would expect you to know. It's a network of fully connected neurons. This is one way of creating a model where we tell Keras, hey Keras, please create a model with two dense layers of these dimensions and having the following activation functions. You could also incrementally build it. So you could initialize a sequential model like so. So model stores a sequential model. And then you could add these layers by using model.add. To go from there, you'll have to build the model, and then you can take a look at the weights inside of the model. So that is one way. Another way of building a sequential model. Again, we're talking simple things. So we're looking at what's the simplest way of doing that. I really like model.summary. So if you print out model.summary, it can tell you actually what's going on inside of the neural network. It can tell you how many parameters exist, how many trainable parameters are there, how many are non-trainable, and all of the little details inside of the model architecture that you've defined. Could someone kindly confirm if this text size is good for everyone, please? I'm assuming it is, but if it's not, please let me know. This, I think, also exists in PyTorch. When it came to PyTorch, I was really happy about this introduction, but I think it's being deprecated now. I just want to double check. It was called named tensors originally. I'm on the PyTorch documentation, and I wanted to point out that this. I think PyTorch adopted this from Keras. I'm a fan of both the frameworks. I'm just learning both of them. In PyTorch, you can also name your variables like so, or your tensors like so. I don't want to confuse you all with the jargon. So the cool thing in Keras is you can name your entire model. So you can call this chai model as well if you want, or just leave it on the default name also. I think Keras picks a default name as well. Yuvraj, thanks for confirming. Yuvraj says the text looks good, so I trust him. Um, you could name the model followed by individual layers as well. So when you're adding a layer, you could pass on a name argument. It's optional because I know that because I've looked inside of the documentation. This is why I encourage you all to play with the documentation as a reminder, which I'll keep doing throughout the entirety of this lecture series. And then you can finally build the model. And then when you print out the summary, it'll tell you, hey, you call this model your example model. Your first layer, or your first layer, which you call my first layer, is actually a dense layer having the following output shape and has these many parameters. Now, code is read more than it's written, right? Code is meant to be readable by humans. So these little details, you might not want to do this. We've all been there where, you just want to get the thing to work and you don't care about adding doc strings in Python. You don't care about adding some documentation. But as a favor to yourself in the future, consider using these features. That's why it was pointed out in the book. Code is meant to be read more than it's written, even by yourself, even by your teammates. These features are useful, really useful for that. So consider naming your models or layers whenever you can. Or if you're doing something fancy, like I expect your teammates to be smart enough. This is basic stuff. I hope everyone knows that. If you're like trying to have something together that just might work, Probably that's a good place to name what's going on, or at least leave some form of hint for yourself. So one thing we need to do before printing the summary that we haven't done in this approach is we need to tell the model what could be the input shape. And for that, you can create a input tensor. And I think this is called a pointer input, if I remember correctly. I want to share the correct jargon, but I believe it's called a pointer input. So we just tell Keras, hey, this could be the potential input. We're not telling you what it is. We're just telling you what it looks like. And that's important for a neural network to actually work, as we've learned, because it's matrix multiplication and that needs to work on a certain dimension. It can only work on a certain dimension effectively. Not effectively, actually just work on a certain dimension. So then from there, we can again print the summary. That's one of the ways where we create a model. You could, of course, pass in activation functions like so. So what we've done in the previous, between the previous and this line of code is we've created a model that just had this input layer and one dense layer. So the input tells us what would this layer expect, and then we can add more layers to it, and hey, that does work. It does tell us that you've added one more layer if you look closely between the differences. So this is one of the ways of creating model inside of Keras, the classic API, the sequential class. The next way to do it is using the functional API. I want to say, I think if you've worked with JavaScript, I believe you might be familiar with this, or if you've watched the JAX series, you might be more familiar with having taking this approach. I was quite new to it when I started playing around with JAX, but if this feels a little non-Pythonic, that's totally fine. I want to just point that out. Sorry about that. So the next way to create models, again, we're doing the same thing over and over again. We want to learn how to create models using different approaches inside of Keras. So that's what we're doing. We looked at the sequential class. Now we're looking at the functional API, following the same simple example. So we define our input again using keras.input, and we tell the shape like so. This is one thing I messed up while trying to replicate the implementation. This is a way of telling Python that you don't want to specify the second dimension. So that's what 3 comma nothing tells Python. Again, little detail, but it's good to know. You could also leave it like so, or just leave it like that if you're a cool practitioner. Now that we know we can name the layers, we will be naming them. So we tell Keras what's the name of this layer. Then we define the features like so. Key thing to note, we are passing the inputs this way. So we define the layer and then we pass on the inputs. Sorry, we don't pass in the inputs, we tell or we connect these like so. The reason for doing this approach is, let me switch sharing and connect my writing pad real quick. I want to point out one minor thing inside of the book. This is known as a graph. They Francois mentioned this to be a graph. It's not a graph neural network. That is something completely different. This is referring to how we actually draw these graphical structures inside of a network architecture definition. So if you're, let's say, defining a model, right? Let me pick a pen. Let's say this is your input. This layer is layer 1. This would have a bunch of neurons, right? So your input goes from here to here. And then from there, let's say it goes through an activation function from where it goes through let's say more operators, or it goes through some form of CNN. I don't think this is a valid architecture, but for the sake of creating this graph. So the thing to note here is, this is the graph we're talking about. This is the type of model that we're trying to build. And this is how, at least in my head and many people that I know, visualize these models. So we're trying to find an anecdote similar to this, right? How do we do this in code? Because again, everything we want to do should be doable in code and understandable in code, right? So we take layer one, we define layer one, and we tell it, hey, this is where this stuff is coming from. We take layer two and we tell it, hey, you connect it to layer one. So now we're building this graph. Again, not a graph neural network, but this graph of the model. So let's go back to the other screen, which I'll painfully reshare. I'm on a roll today. Usually I take too long to switch sharing screens. There we go. So that's what we are doing here. We can print out the input shape, we can print out the types, and we can print out the model summary as well. So if you print out the summary, it's again a similar model as earlier. The only difference here is we're using the functional API to define the model. So when we call the model, we'll have to pass in the inputs and the outputs, because right now the state is not being stored. And that's how we do this. So again, similar model, nothing fancy here. Now, if you want to work with a multi-input, multi-output functional model, that is possible as well. The reason this chapter and this collab exists is we're trying to go from this simple example that just works out of the box to something that's a bit more complicated step by step. So we want to incrementally expose ourselves to different problems and how can we tackle them, right? So we do that by using the functional API again. Sorry, I am trying to see if there are any questions. I always get distracted by that. Someone's asking what is the reference material. There's no reference material. We're using the official GitHub repository by Francois Chole. So if you look up deep learning with Python, GitHub, we're using these notebooks, and I'm just providing a revision or a highlight of different chapters. We're not strictly using the materials on the books because this book is not freely available, and I expect everyone to own a copy of this. So we're going through these chapters in a sequential order, and we're on chapter 7. I hope that answers your question. So now we're on this problem of having multi-input and multi-output functional model. So I think inside of the chapter, they talked about what if you have a bunch of words and other inputs that you want to tackle. So it's an NLP plus tabular problem if you want to strictly put it into a bucket. You could take an input of the vocab size, and you could take an input of the text body, and you could take an input of the tag. So now we have these three inputs. Again, if you go back to the graph we drew, this time we would have three circles for the input, right? Again, that's why it's really, to me, it's, as I speak this, right, it's really simple to visualize in my head. Three circles that connect to three layers, possibly, or beyond. So that's the graph we want to be visualizing in our head. Just take a paper every time you want to implement something like this, draw that, and then it's really simple to implement in Keras, right? We can define the title, text body, tags, like so. All of these are inputs. So these are Keras input that have the shape like so, which we've defined above. And for our co-workers' mental health, we can give them names also, or to remain in love or in harmony with them, we can give these names. From there, we can concatenate. So let's look at what this does. If I can find it. What does concatenate layer do? Layer that concatenates a list of inputs. It takes input as input a list of tensors, all of the same shape except for concatenation axis, and returns a single tensor. So let's look at what's going on here. Let's take a look at this example. If we concatenate x1 and x2, which would be these two layers, the shape becomes a stacked model of these, or they get pasted together. That's what's going on here. So now we can take these three different inputs that we just defined and concatenate them together. From there, everything is hunky dory. Now we continue with dense layer. We pass in the features like so. Since we've passed in the input already, next thing we take the priority and pass in features further to this layer. And from there, we define another layer called department like so. I apologize. These are the outputs. Features would be the middle layer. So these three are the input layers. I actually drew the graph and confused myself. Let me start again. So we have these three inputs and we have these two outputs. So we want to predict the priority and department based on vocab size, number of tags, and number of departments. And we have these hidden layers. So we pass the input to the hidden layers, which we call features. And then we pass the features to the layer that will give us the outputs. And then when we create the model, we pass in the inputs and outputs in a list like so. Saurav is asking how parameters are calculated in model summary. Um, let's see if the documentation tells us much. Sorry about that. Summary method prints a string summary of the network. It doesn't tell us how that is being done. So we could take a look at the source code. But quite simply put, if you are to draw the graph of this model, a dense layer actually just contains all of these models connected to each other. And if you take the size of the tensors, so remember when I said the input image is 2000 by 1100 approximately, it's actually 1920 by 1080. I know that through a painful bunch of editing work for my podcast, if you multiply those numbers, that gives you the number of parameters. So assuming your PC is learning this image, or this is the size of the image that is being learned, the number of parameters would be the number of elements inside of this tensor, which should be 1920 by 1080 by 3. And if there are a lot of these, you multiply by that number, that's the number of parameters that are being learned. So when you use model.summary, that's how you get those numbers. That's where that number comes from. Thanks for the great question, Saurav. So now we've created this model that takes three inputs, gives two outputs. How do we train this? Right? We've just defined the model. We can check if it's created by printing the model summary. We'll have to define a few things. So we define the title data like so, where we define it by creating a randomly initialized numpy array, which has the size of samples and vocab size. We define the text body data as well and tags data. So we define, for the sake of this toy example, randomly initialized inputs that would correspond to these three inputs. And then we define the priority data and department data from where we compile the model. So we pass on the optimizer, we tell it, hey, these are the loss functions we want to look at, and then we pass on the matrix. From there, we fit the model, and then evaluate it on a particular data set. And then we can print out what's happening inside of the model. Now, this is quite painful, right? Because you need to pass in things in the right order. So when you're fitting the model, this should correspond with the title data. This should correspond with the NLP data. That's not how things should be, right? Now this is getting out of hand really quickly, because like assume you have 50 inputs. That's really painful. ImageNet has, I think, about 1,000 classes. I might be wrong about this. It might have more. So ImageNet 1K, I believe, has 1,000. ImageNet 22K, I think, has 22,000 classes. What if you have to pass that? Would you write this? No, you won't. You'll read in a dictionary. So again, this, I want to point this fact out. If you're new to Python, dictionary is a way of telling Python, they, hey, this is the title, this is the key, this is the value. So you create these mappings. If you're from the world of computer science, the only place where you can flex your knowledge would be calling this a hash map. Again, in Python, it's a dictionary where you tell Python, hey, Python, please store this data as title, please store this data as text body, so on and so forth. And then you can just take this and pass it to the model when you're working with the model. So you can simply pass in the dictionary to the model. Anything defined inside of curly braces in Python would be a dictionary. So now, this is a cool thing that I learned while reading the book. But Keras also has a nice utility that lets you print what's happening inside of the model. Really useful again. So we have a title, a text body, and tags, which go to this concatenation process, after which they are passed through dense function, which gives us these two outputs. So we've created this multi-input, multi-output, more than one, right? That's multiple model. And if you want more details, you can pass in a flag called show shapes true. Again, this comes from keras.utils plot model. If you want to play around, copy this, look inside of the documentation, see what possible arguments exist. Or you could simply also print out the layers like so. So that is another way of creating a model inside of Keras. Let's see. I think there's more details around this, so I'll continue further. Any questions so far? If not, we'll continue with subclassing. Awesome. I don't see any questions yet. Also, there's a small lag with YouTube. So your questions might have gone through, but I don't see them because there's this small delay that happens. I'll come back to them when I see them. So now we're on this journey of understanding the possible ways of defining models inside of Keras. And we've looked at how to do it with sequential API, the functional API. Now we look at something that's, if you come from PyTorch, it's similar to that. So we're subclassing the model class. In computer science words, it's called inheritance. So we inherit from the model class. And whenever you inherit any class, you have to initialize the superclass constructor. So what is a superclass? When you inherit from a class, I have inherited genes from my parents. That's the parent class. I am the student class that is inheriting. In Python, you would have to initialize the superclass parameters like so, because I've inherited from this class. That's a object-oriented programming concept. Don't go from here and try to look up OOP concepts, object-oriented programming concepts. If you're new to programming, or if you're new to these concepts, or if you've been coding for a while and this is the first time you're hearing this, this is not the place to go on a tangent and learn about that. That's a rabbit hole that ends on lead code. And that is a dark path. So remember, we're here to learn Keras, and this is one thing that you'll eventually start to get a hang of. So we call the super init which actually tells Python to please call the init of Keras models. From there, we continue our regular journey of defining concat layer. So this is a parameter of customer ticket model class where we tell it, hey, this is a concat layer which concatenates stuff. Sorry. Then we have a mixing layer, which is dense, a dense layer of dimension like so, an activation function like so. Then we have a priority scorer and a department classifier. Now we need to define a function call, which means whenever we call this model, this function will get executed. So we tell the inputs, which are title, text body, and tags. And then we create the features like so and outputs, which would be priority and department. And then we return them from the model. So now when we create an instance of this model, call would get executed and we'll pass in the number of departments to it, from where we can pass in or retrieve the output, priority and department like so. Again, the names don't have to match. This could be just T, this could be P, or whatever. We're just doing that for readability. And we'll pass in the title data, text body data, and tags data to the model. That wouldn't train the model itself, right? Because we've not done any training function here yet. So we'll still have to compile a model and fit it and evaluate it. Again, same thing so far. So this is how we inherit and create a subclass model inside of Keras. This is the third way of creating classes or models inside of Keras. I think from there they go into how to create a functional model inside a subclass model. This is quite straightforward, so I'm skipping that. I have quite the agenda to cover today, so I'm skipping ahead to a few things. We also learn later in the chapter of how to write our own matrix. So we define root mean squared error, and I'll leave you to reading this bit. Again, this was quite readable to me, and I'm the benchmark. If I can understand anything, I'm sure everyone reading the book can. So root mean squared is actually the sum of square root of the squared differences. I'm again on the verge of actually covering this, but let me just point out the functions here. So we square the differences. Just look at this line, please. We take the square of the differences, and then I believe we take the square root of it. That's all you need to know. But again, if you look at the mathematical definition of root mean squared error, you can define it inside of Keras matrix. One thing to point out here is if you actually go to Keras matrix, it has a lot of metrics implemented. There are accuracy, probabilistic, regression, classification, image segmentation. Sometimes, especially with a few Kaggle competitions, you have these tricky bits where you have a completely different metric that you want to work towards. So for that case, you can define a custom metric like so. Root mean squared error, I'm sure it does exist inside of Keras already, but this basically shows us how to create a class. So we create a custom class like so, where you'll have to define how the metric would update its state, how would it reset itself, and then you pass this class to the list of metrics that you pass your model. That's about it. Now the next thing inside of this chapter is callbacks, and this is how I remember callbacks. So callbacks in code is quite similar to callback in real life. Please call me back when. Please call me back if you complete the homework of Keras study group. Please call me back if your accuracy starts to drop. So that's what callback does inside of Keras. If you're new to callbacks, it takes a small while to get used to it. It just tells the model to call back the executor, the Python executor, depending on different conditions. So the reason for these things to exist is once we kick off the training, it's really hard to understand what's going on inside of the model. These callbacks help us, first of all, monitor what's going on inside of the model and also change different things. So, assuming you want to actually change the learning rate or things like that, or if you want to early stop your model. So, let's say if your model is overfitting, how would you know if your model is overfitting? The accuracy would start to go down. You don't want to train your model beyond that because it's starting to overfit. So you need to stop before that. Early stopping is if your model is starting to overfit before your number of specified steps or epochs is complete, please stop the training. I don't want to spend more money on cloud credits, cloud compute. Please, Keras, stop the training. So we pass a callback called early stopping, which takes care of that. You could also checkpoint your model, which means, hey, after every single epoch, Keras, can you please save my model? And Keras will do that for you. No problems. So when you're fitting your model, you pass it this callback list. Right now it's early stopping. Let's take a look at what that is. Stop training when a monitored metric has stopped improving. So you can tell Keras, hey, I have the patience of 2 epochs and I want you to monitor the validation accuracy. If it doesn't improve beyond 2 epochs, I will lose my patience of spending more money on GPU credits. Please stop the training, and Keras will do that for you. So this is how you can do it using a simple callback. And we pass this callback list to Keras. You could write your own callbacks to perform different functions or different activities. And these can be performed when, hey, call me back when training begins. Call me back. This is how I remember it in my head. If anyone in the audience has a better way of remembering it, please let me know. But I just have this analogy that I built. So call back on training beginning, call back on batch ending, call back on epoch ending. And you can do different things with that. That's what we learn inside of this. I wanted to do a walkthrough of how you can use the WonDB callback to log your experiments. So this comes from if you've logged into or if you've ever created an account inside of weights and biases, you can check out the integrations here. We work, weights and biases integrates really well with Keras. So all you have to do to track your experiments is just pass on the weights and biases callback. So weights and biases is an experiment tracking tool that is quite useful and a lifesaver when you're doing a lot of experiments. Inside of the book, TensorBoard is suggested. I would suggest you to also check out weights and biases. It does a few things beyond that. You can track your experiments, you can version your data sets, you can evaluate your models, you can optimize your models, and then you can also write reports around it. So it basically is the perfect collaborative version for software 2.0, if I may. Now, the only thing you have to do to get all of this data, right, when you're training your model and you want a nice summary that you can share with a coworker, I'm trying to find the link to the dashboard that this would have created for me. My apologies, I can't find it among the list of open things. This is the part where I embarrass myself in front of everyone. um, I think this was the one I ran. Yep, there we go. Um, Maybe I'm confusing myself again. Sorry, give me 1 second to quickly find the correct dashboard. In the meantime, I see a question. Will it save the model weights after two epochs of patience or when it stopped improving? So that depends on how you define. I assume you're asking about the um, callback where we're checkpointing the model. I'll share the documentation and you can take a look there. That depends on how you define it. It'll save the model at every epoch. So it'll be saved quite a few times, but you'll have the benefit of having a lot of not going back a lot in time to find the correct model. I found the correct dashboard, so I'll go back to sharing that. This is the risk I run of embarrassing myself, but I'm happy to do that just to host a lecture every weekend. So here's the nice thing about tracking experiments. If assuming you have a lot of these, it's really easy to visualize how things change with every epochs, how your validation accuracy is being changed, or what examples are you working with. This doesn't look like a frog. It's quite terrifying to me. This looks like a German Shepherd somewhat. Don't worry, your YouTube connection is fine. These images are pixelated because it's CFAR 10. This definitely doesn't look like a frog to me. It's probably a bus. But again, it's this visual process of understanding what's inside of your model, right? So you can do that with weights and biases. And I'll point everyone to check out the 1db callback, which you can pass inside of the model fit loop. Again, that's there in the examples. I wanted to run through this, but in interest of my ambitious agenda, I'll continue going through the collabs. So Harpreet, let's uh, answer your questions. Your question was around model checkpointing. I see it there. Um, and in the meantime, let's highlight this. So callback to save Keras model or wait at some frequency, right? Whether to keep the model that has achieved the best performance so far, or whether to save the model at the end of every epoch, regardless of performance. So I apologize, I misremembered. You have the option of sharing the best model or the model at every step. Definition of best would be which quantity you want to monitor to be maximized or minimized. I hope this answers your question and I'll continue. But if it doesn't, please interrupt me again. Awesome. So we've understood how we can monitor and visualize as experiments using a simple callback. And we've understood what callbacks are. We've looked at how to create a model using sequential, functional, and subclassing approaches. So let's continue further. From there, we write a complete training and evaluation loop, which I'll skip because it's quite straightforward. You can also read the chapter further to understand how to write a step-by-step evaluation loop. The thing I want to point out here is you can call tf.function. What does this do? This, especially with your model definitions, tells TensorFlow actually to compile your model ahead of time. This makes it run a little faster because instead of running it in an eager mode or in an interpreted mode, it compiles the model ahead of time. If you come from the world of, I want to say, uh, I want to say Jax, but Jax is a little different. If you come from the world of PyTorch, it's similar to jitting things. I think PyTorch derived the inspiration from here, again, without going into the too political details. But it's, again, it's similar across all frameworks. So what's going on here? We're telling TensorFlow, please check out this model and do whatever you can to make it run faster. So the software engineering team behind TensorFlow has written very smart code that knows things it can optimize. It goes ahead, compiles. So internally, TensorFlow looks at your model. Hmm. I see matrix multiplication. We can do that faster. I'll use a different approach internally to train your model faster. Hmm. There's ReLU that can be made. I'm just throwing stuff off my head, but here's an approach. We can compile it to make it run faster. All of that happens behind the scenes. You don't do anything. You just write this decorator at TF function, and things are taken care of. It's easy to write this everywhere, so I don't have a good suggestion because I'm learning myself of where and where not to use this. But if used correctly, it can speed things up. Um, awesome. So that's the end of chapter 7. Any questions so far pertaining to this? When we will not use this approach? Harpreet, I have spent more time in PyTorch in my life. And even there, I don't know where not to jit things. Many times I forget to jit things. That's the honest answer I have. So I don't have the best advice here. I'll try to find an answer through the Keras experts I know. But off the top of my head, I apologize. I don't have the best answer to this. Even with Jax, I think this is easy to PJIT everything there. It's called PJIT in Jax. We have a Jax study group if you want to learn from there. So the next thing we learn is we just studied about convolutions. I showed it to you inside of Microsoft Excel. I showed it to you visually as well. We learned how different layers learn, what's happening inside of them. Now we'll do the easiest part, which is we'll learn how they work in code. Also have this blog open, which gives another quick reminder. This is how the outputs are performed or calculated from a neural network. Thank you, Irhum, for this blog. So a CNN builds the outputs inside of the model like so. You don't have to worry about doing any of that because in Keras, you just import the layers and you throw in conv2d layers followed by max pooling. Do that a bunch of times and your model is ready. So the theoretical knowledge is important because you need to understand how these works. Remember, we looked at the kernel sizes, we looked at the activation, we look at the number of filters. It's important to know these, but inside of Keras, it's really easy to implement. You just create a conv2d layer, and that's a convolution layer that has filters stored inside of it that perform the action that we discussed earlier, and they basically take care of all of the things we were concerned about. You can print out the summary, of course, take a look at all of these details. Inside of the chapter, again, glancing over the details, we prove the point that these perform better while using lesser parameters, right? If you remember my slides, I claimed that fully connected models use more parameters. So I think GSS had asked this question. It's their alias, I assume, of how do you find those parameters. I would encourage you to create a fully connected network, see how many parameters that has, compare it with this and compare the accuracies. That's what we do inside of these chapters. We understand border effect and padding, which I'll quickly explain, or maybe I'll leave to the next bit. And from there, I believe the chapter goes into image augmentation. So I believe I'll jump towards explaining image augmentation next. Further in the chapter, the thing I'm skipping to come back to later is how do you read in these images? Because again, it's all numbers, right? How do you feed this data effectively to a model, you could have millions of images. And have you tried copying a million images? Have you tried that? Windows just crashes. You just don't see the time. It's always calculating. How do you do that effectively inside of a neural network? Is also important to know, right? You could read it from a dictionary. There are different approaches. Of course, there would be functions that do this in a very optimized fashion, right? So this is one of the ways where we can use a Keras utility that imports from the directory, and we can simply pass in the input data set. Many times you have in the real world, especially, you have this problem of not having the data set in the right function. So now you have two problems, right? Either you put the data in the correct format, sure, and then just use a utility, or write a custom dataset class for doing this. So there are two sides of things to this problem. um, we'll come back to the dataset class, but now I want to point out image augmentation. So I'll do that. I'll give a presentation of image augmentation using the documentations of augmentation. This is a framework by really smart people who've won Kaggle competition, who are working at incredible industries, and it's being used across many amazing places as well, many amazing industries. I believe it does a lot of great things. It's called albumentations.ai. It works really well both with PyTorch and Keras. So I see many of our community folks. I see Yuvraj, I see Mayank, who've been with us in the PyTorch study group as well. We learned about albumentations there, and since it works with Keras, we'll also look at it again now. So Ayushman, who is I think a Kaggle expert or master, he gold medal in a competition about which we learned from him. He's created this nice demo that lives inside of the documentation. So we'll use that to understand how to work with albumentations in TensorFlow. The reason we want to, first of all, do any of this is in the last case study, we studied about we could always get more data to make our life easier. If you don't have more data, you can create more data. How do you do that? By changing the image ever so slightly. So you take this image that you're seeing right now, and if you're trying to build a Siam detector, you can rotate this image. You can twist it by a few degrees. I'm twisting myself. I can't, or I actually can rotate my webcam, which I won't dare to do on a live stream. Those small changes are enough to improve your model a little bit. Our end goal is to be able to, let's say, detect me in any image. If I'm always in the center of this image, first of all, that model doesn't work well. So there's a problem with what we call generalization. To tackle that, you could cut this image off in the right hand corner. So here's, here's like a irritating way of doing it by just covering it. But you could just paint all of these pixels black. So you need ways of doing that, and albumentations is a framework that allows that. Keras also has augmentations built inside of it. So here are the input images. I won't go into details of, hey, here's what's going on inside of the code. I leave you to understanding it. My goal here is to explain what augmentations are. So we read in all of these images. I see sunflowers, I see flowers, I see a person with a sunflower. Interesting. I see a dog with a sunflower. Is that a dog? I apologize if that's a human to the human inside of that image. So we build pipelines that could do a lot of things, right? I mentioned earlier you could rotate an image. So you could rotate the image by a few degrees. You could change the brightness. by 10%. That can do wonders for your neural network. Again, it's all just numbers, right? That your model is fitting or overfitting to. So to work with those or to take care of those things, you can change the compression, the hue saturation, you can change the contrast, you can flip an image horizontally. That's one thing annoying. I'll confess this in a live stream. Have you ever tried shaving? This has happened to me in my college days. Have you tried shaving with a Zoom call? Like a Zoom meeting where it's just you by yourself? The image gets mirrored. So it's more difficult to do that. Or in your sometimes with your phone, I want to say that happens. And if that's enough to confuse your humor brain, it's good enough to confuse neural networks as well. So we create more data by horizontally flipping it. You could also vertically flip it. The next question becomes, when do you want to do what? So if you're working with text, right, you won't want to flip it at all because that loses its meaning. So depending on what problem you're working on, you need some amount of domain expertise, I want to say, to be able to understand what to perform. So you can do all of these transforms inside of the model. And let's see if these are printed out. I might be mixing the PyTorch and Keras example in my head. So no, these are not printed out. So to showcase another example, I will go to a blog that I had written. Again, my goal here is to tell you about a few image augmentations that exist and for you to explore them. So I wrote this blog post that you don't need to read it. Honestly, spend more of your time writing this in Keras. It's a waste of time to read this blog. I'm giving you enough gist that you just need. So here are a few suggested image augmentations that are possible across different frameworks. I'm not focusing on the framework. This was inside of FastAI, but here are the possible things you could do in FastAI. Try to do this in Keras suggested homework. You can rotate your image like so. Our goal is to create more examples for the network to learn from. So one of the possible image augmentations is rotate. Let's see if Keras has that. Um, Let me move this tab closer to the documentation. Go here and see if rotate exists. And notation layer. Okay, find it. We found it. So this is inside of image pre-processing and augmentation. Looks like we found that layer. So we can also do rescaling, center crop, and a bunch more things, right? So as you can see, these also exist inside of Keras. So you can rotate your image. A real world use case of this would be if you're working with a secret agency trying to find all of the swimming pools in your area. With satellite images, rotation actually helps improve the accuracy, as you can see. You can make a cat a trippy cat. For certain use cases, this might help. I don't think for this cat detector it's helpful at all, but you can change the colors. You can adjust the brightness. So if you observe that, the images existing inside of your model all just have too bright pictures, you can change the brightness to a lower value, or you can just play around with the value still, and that's helpful towards the model for certain cases. My example was I was trying to segment text from a background, and actually sometimes changing the brightness is helpful if there's a bit of shine on the text. You can change the contrast. So the example would be if you're trying to segment text, increasing contrast most of the time is really helpful. You could crop into your image, you could crop and pad the image. So we crop inside of the image and pad with zeros, so that's black. My painful chemistry classes always remind me of a dihedron which has 4 angles, 8 angles. See, I still don't remember that. You could rotate your image using a dihedral transform. You could add jitter, which is like adding noise. If you remember the OG days of watching television, um, This is how a distorted television would look like, and that's what jitter does. It just adds jitter. So these are a few. I have more in the blog, but these are a few possible image augmentations that exist in FastAI. That's a PyTorch based framework, but these would also exist in Keras, or I want to say Jax, but I don't think they might be in Jax yet. Again, the goal here was to understand how image augmentations, first of all, what they are, how they work, and why are they helpful. So if they are helpful, is for you to figure out, play around with the dataset, add them, and see if it helps. It's disappointing sometimes to see it in practice because the improvement is really small, honestly speaking. Um, so that's how image augmentations work, and you can, of course, call these from Keras layers as well. I think this is a good point to pause our adventures. I apologize because I had again set this very ambitious agenda and we got into answering questions. So we're stopping before implementing a cutting edge architecture. But I'll give you enough of a teaser if I can. So this was done by Shomik, who is my colleague at Bits and Biases. Shomik has been doing incredible work in the world of Keras. He's really smart and he has been contributing to the examples inside of the Keras repository. You should trust him much more for implementations around Keras than you should trust me. So Shomik has written this code that he trusted me to steal from him, which I did. This is a cutting edge architecture that got a lot of hype. I don't expect you to be able to read this code, but I want to point out a fact that hey, nothing fancy is going on here, right? We see the similar imports that we've been working with. We just define a conv block inside of which we use the functional API. We do a few things. We write a few conditions. We define a few more blocks. Block inside of a model is a collection of layers. We can define an initializer and then finally build the model. So just using these few lines of code, again, rushing through it, we'll come back and take a really deeper look at this. Shomik, I believe, hasn't published this yet, and he will publish it soon, of course. Um, just by doing all of these steps, you get one of the most recent architectures implemented in Keras. So I'm not a motivational speaker, but I hope that was motivating enough for you to understand that we're at this point where we can build really good CNN models. We've learned enough. We, of course, don't know what this model is. I didn't give you that context. That's on me. I didn't tell you what's going on inside of this code. We'll come back and understand that. Hopefully, by then, Shomik would have written a really good blog post, so I really don't have to do anything. Uh, I will try to wrap things up from here and suggest a few homework. So we have gone up until I think the initial bit of chapter 9, where we know a few things about computer vision. Next time, we'll be taking a look from chapter 9 to 11. Again, ambitious agenda, I know, but we'll also try to cover next. Homework for you all, implement a CNN architecture in Keras. I hope I gave the motivation that you can actually build these things. We looked at 4 cells inside of a Colab notebook written by a very smart person, smarter than I am, which can implement this model. I would encourage you to start something to Kaggle. I think Francois gave you a taste as well inside of the chapter. It's the most addictive thing in machine learning, if not machine learning itself. Uh, this is a point where you can start playing around with Kaggle competitions as well. So go to Kaggle, see if there are any image um, competitions that are of interest. I see a few questions coming in. I'll address those before ending. Play with augmentations. Try to log experiments with weights and biases, and try to translate models from PyTorch examples to Keras examples. These aren't good PRs. These are just for your practice and practice. or spending more time in a collab or your own Jupyter notebook is how you'll get better at, I believe, writing code in Keras. Consider sharing these learnings in 27 days of Keras. Again, we at Weights and Biases are happy to send swag every week to people who write good blog posts. There's no agenda for us here. We genuinely want all of you watching this from the community to spend more time learning, and this is just our way of trying to encourage you all to participate more in community activities or trying to create more content. So let's go through the questions real quick before we wrap up. I know we're over time, so I'll try to wrap up faster. Ankit is asking, do we prefer to have a balanced data set as well as good data so that our model is well trained? With augmentation, we are distorting the data, making it messier. So would too much augmentation spoil the data? That's a great question. And again, it'll come through practice, right? You can only find these answers through practice. Usually, unless it's a very small data set, so where you have like one example versus 1,000 examples, things get really interesting. You might want to look into Siamese networks. Try that out. This was the last thing I knew. I'm assuming many new things would have come up. With augmentation, again, yes, you could, of course, totally mess up the data set as well. In practice, you apply this to like a fraction of the input and you applied like in a very small percentage randomly. So it like, if you read any paper, it like gives you a boost of at best 1 or 2%. Again, that's where this starts to come into play. So great question. Again, it you can only find the answer through experimentation on your own data set. What writing pad am I using? I don't remember the name of this. I think I just went to Amazon and searched for writing pads that work well with macOS. I'll try to find the answer and share it with you. I'll maybe have to check my order history. I see a few questions from earlier that Yuvraj has answered. So thank you, Yuvraj. I don't see any other remaining questions. So again, thanks everyone for joining. I'll see you next week. We'll learn about ConvNext, implement uh, or go through the implementation by someone smarter than me of the architecture in Keras, and we'll try to learn about time series as well next week. I see one final comment. So, Yuvraj has answered your question, I believe, Ankit. So thanks again, Yuvraj. Awesome. We'll meet again next week, same time. Consider doing the homework, consider writing a blog, consider sharing it with the community. Thank you for joining again. Let's meet next week again to continue learning Keras, and thanks for your time.